In this assignment, we focus on analysis based on the general concept of spatial proximity. After opening GRASS, I will keep working in my assignment 3 map set, but you can create a new map set as indicated in the instructions. As before, let's first change to working directory, where I have already downloaded all these text files with different tables and rules. So CD, and I have this directory, homework 3, where I have already downloaded these text files. So please do the same. And then we can start with the first part of this assignment. So we will use buffers to find developed areas which are potentially impacted by noise from highways. So we will be working with land use map. So let's just first set the region to our land use map. Then we will be creating buffers around the major roads, but we will be using the raster tool for buffers. So that's why our major roads need to be represented as a raster line. We have done this already. So in your in the permanent map set, there may be the raster representation of roads, of major roads, but let's do it again so that we have it in our map set. And I will also indicate the resolution of this raster representation in the name of the output. So here we have the raster representation of major roads, and we will create 3 buffers at 3 distances, 250 meters, 500 meters, and 2.5 kilometers around these major roads. And so now we have the buffers along these roads at these ad hoc distances. You can select different distances. Let's say if you have good information about the how far the noise can travel from these roads in these areas. So feel free to do that. But these are the ones that are selected for these instructions. And then to extract the developed areas within these buffers, we will use map algebra. So you already learned how to use it. The developed areas are category 1 and category 2 in our land use map. We have already learned that in our previous assignment. So we will extract these 2 categories, and we will put roads buffers in those locations where we have these categories, and everywhere else there will be null data. So let's see. And then we will assign a color table to this to the extracted map. Keep in mind that when I run map algebra, the output is not in the not displayed. So you either have to actively display it, or it will automatically display when you change its color table. And then what we also want to know, because we need to get the area, the developed area, we need to write r.report command that will compute the areas in each category. And that for that, we transfer the noise categories into that file using the category text file that we have in our current directory. That's this noise category txt. Let's see what we have there. So you can see one is, so we are labeling these categories as a source, high, moderate, and low impact. Okay. And then we can run our report. So you can see that in the source, we have source is really the raster representation of the road. High impact is the 250-meter buffer. So we have quite a big area in that. It's 23% of cover. So this is the one that we will want to report. So let's create the output map, and I can erase what I have there. So just to start with a clean slate, or you can just switch off those layers, and we will just create the output. So these are just the developed areas within those three buffer zones. Then we will add the streets, and then we will add the legend. And you can adjust the size of the legend. We already did that many times. And add the bar scale. And let's save this map. And don't forget to answer the question, what is the total developed area in hectares within this first 250-meter buffer? So now we know that there is a substantial developed area around the major roads. Let's use the buffers to find out how many schools are actually built close to the major roads. And very often what happens that these schools might have been built before these highways were built. So for that, let's again convert our input around which we will be doing that we will be using this analysis into raster, so that we can use raster-based analysis. Then we will use map algebra to find those schools and the capacity number of students in those schools that are close to the roads. So let's go through this workflow. So we have now the schools there represented as raster, and you can just check it by switching off this. So they are very small now because our raster is much smaller than when we did it with 200-meter grid cells in our previous assignment. So now let's extract those schools that are within the buffers. And when we converted the schools to raster, we used core capacity variable. So we can use this core capacity to estimate the number of students that may be influenced by noise. So then we can run r.univar to find out what is the value of the raster in this data set that represents the schools that are affected by noise. And keep in mind that we are not really interested in mean, because that would be what is the average for these raster cells. We want to know all of them that are there. So I will let you to find out which of these outputs actually represents the number of students who would be potentially affected by noise. Now we can just extract those schools that are affected by noise just for visualization purposes, because you have seen that the raster cells are very small, so we don't see them very well. So let's convert these schools impacted by noise to vector representation, to points. And then we can display them as points. So let's first display all the schools. And then let's highlight those schools that will be impacted by noise. And you can see that we have two of them very close to highways. And then we can add the vector legend. And we already have the bar scale. And let's save this map for your report. So don't forget to answer the question, how many students are potentially affected by noise? Based on the school capacities and the buffer, 250-meter buffer. So let's now move on to application of cost surfaces to find the distance to an accident of on one of these highways, and to find from where the help can get the fastest to this accident. So we will use the concept of cost surfaces, cumulative cost surfaces, and least cost path to solve this task. So let's run the erase to remove the previous layers from the display. And also we won't need the this legend, but we can keep the bar scale. And let's create first the cost surface. So what is the cost to our first map that we will create is the cost of passing through a grid cell. So let's set our region and resolution to predefined resolution, that's Southwest Wake, at 30-meter resolution. We can zoom to computational region. You will see that it's essentially the same that what we had. Now let's look what kind of categories we have in the streets wake vector layer. So you can see that there is a lot, and that's because we need these variables if you want to, for example, build a network network topology and do routing along the vector file, but we will be using the raster representation. And because we want to know how fast the cars can go through through these roads, then we will use the variable speed, which is here, to convert these major roads to raster. And recall that in the previous task, when we did the buffers, we used the value. So we just converted all the major roads to the raster using the value 1. Now we will be assigning to our raster the value that represents the speed limits. So let's do that. So now you can see that instead of having just the yellow color, like what we had for the major roads, now we have for all of the streets and major roads the variable color based on the speed limit that we found in the vector data layer. But there are nulls in between. And because, for example, the fire stations, schools, and many other facilities, for example, shopping centers, are off the streets, if we want to do routing from these facilities, we also need some values that are off the streets. And we will just assign value 5 miles per hour for all of the off-street areas. And we will use map algebra for that. So if the map is null here, then we will replace these nulls with 5 miles per hour value. And we will just check what kind of values do we have in this output raster. So it's between 5 and 65. We will color the output. And so you can see and then we will add the vector file for streets. And let's put there the legend. And with the legend, I see that I would prefer inverted color table for these. So let's change the color. So we have this color table, but we want invert colors. So let's just run it. Okay, that's better. And I don't need this one. So we can save this color, which represents the cost of passing each of the grid cell. Now let's input the point where we have the accident. And I already downloaded it, and I have it in my working directory. And we will display it later. And now let's convert the speed limit into the cost, into the time, into travel time. So we have the speed limit for each grid cell. Now we will convert it to the time that it takes to travel across each grid cell. So we use map algebra for that. And once we have this cost, then we can compute the cumulative cost of how much time will it take to get to this site of accident from any grid cell in our entire study area. So let's just run that cost. So now you can see this is the cumulative cost map. Now it would be really useful to display the point so that you can to highlight it a little bit. So let's just give it a bigger symbol. And I think I have it like this. Just give it red. And let's put it on top. Okay. And now what we will do to highlight the time that is represented by this raster, we will extract isolines of equal time to get to this point that are called isochrones. So let's work on that and let's prepare the output map for your report. So we will create contours of equal time to get to the point of accident. So now we have those isochrones. Now you can keep this color table. I think it's pretty good. In the instructions, I have changed it to the same color as we use for elevation, but feel free to keep the original one. So this is the streets cost. We already have it displayed. So I will skip this one. I already have the point displayed, so I don't need to add that. We can add the streets to highlight the relation to streets. Oh, I just did okay. That was the isochrones, so we don't need those. We already have them. And then we want to change the legend to streets cost. Let's just use this one. Okay, and we can change it. And we can save this map. So now an important task will be to find the fire station that is the closest to this accident, but not using the Euclidean distance, but following the cost surface. So first, we will create a copy of fire stations so that we can add additional information into the database. into the data table. So we create our own copy. We look at what kind of variables we have that, and I have already created a new column, which is this CV lag, that will include the time to the accident. And now to fill, currently it is an empty column, so there is no attribute values, and we will query the streets cost, the cumulative cost map, to put here the values of the time that it would take to get through each of these fire stations to the accident. So let's just do that. Now you get a warning that there are 56 points, 56 fire stations that are outside our area, but that's fine. We know that those that are the closest will be within this area. Now let's look where all of these fire stations are located. We already have that raster displayed. And we already have the location of the accident displayed as well. So now we want to know which of these fire stations, from which of these fire stations they can get that closest. You can see that there are a couple candidates that are pretty close. So now it will really depend on the not only on Euclidean distance, but also whether they can drive fast on those roads. And we can now use this command vout ASCII, and we can extract those stations that where that variable where we stored the time to get to that accident is less than 0.1. And I will let you know what this 0.1 and greater than 0 actually means in terms of units. And it is in the instructions. So now you get that table that is also listed in the instructions, and you can see that it's the fire station from Western Boulevard that has the shortest time to get there. So now let's find which one, let's extract that value. So here you have that value that we already have seen from the table. And let's now find the least cost path. So we will use the command r.drain to find the least cost path. And we will do the one from Western Boulevard, and the other one is from Holly Springs Station. And that least cost path has popped up here. Here is the other one. And we can just change the color table. You can use other color table just to make it a little bit more visible. I'm not really sure whether that changes anything. And we have already these streets cost in our map. So we already have this map essentially created, so we can save the map. And now, don't forget to answer the question. There are two questions related to this task. One is about the meaning of the constant when we were converting the speed limit to the travel time. And another one is to compute the average speed that the track would travel to get to that to the accident, and to actually get the length of that route. We can use the command r.describe, and that gives you that the track will have to pass through 83 grid cells to get there. And then you use the resolution that you have to estimate the distance. And then we have the other one. So it's really longer, more grid cells that you would need. So that is all, and the final task for this assignment will be in the next video.